Okay, so what we're going to do today is go on with geodesics and look at some of their properties and look at the reason why we care about geodesics. So just some of the basic things. We're going to start with a finely parameterized geodesics. In other words, not only is the geodesic parallel transported to itself and proportional to itself, it's got a constant magnitude. Okay, so a finely parameterized geodesic is a curve whose tangent vector TA obeys this equation. Okay, if it is a finely parameterized. So finely parameterized corresponds to, in some sense, the unit vectors we were working with in 3 space. In other words, the norm doesn't change as you move it along. And we'll also see it's related to the length that you've traversed along the geodesic as well. Okay, and so this is the abstract index notation of writing that down. Remember, this is the parallel transport operator, and then instead of applying it to any vector, you simply apply it to the tangent itself. Okay, and so if you're working on a coordinate basis and you have the coordinates as a function of parameter, then you're going to have the tangent vector is just how those coordinates change as a function of parameter. And you're then going to have that if you substitute that into this expression, it is simply the second derivative of the coordinates with respect to the parameter plus your Christoffel symbols or your connection contracted with the first derivatives of your tangent vector. Sorry, the first derivatives of your coordinate contracted with your tangent vector. Okay, so those are geodesics. And then furthermore, we had that through any point with a tangent vector in the tangent space, these geodesic exists, okay? And they are unique and they don't cross. And that follows exactly from ODE theory in an ordinary Rn. Okay, so now they are exceedingly useful, okay? So the one use, and one of the things that I guess Riemann used them for initially is they can be used to construct a coordinate system on the manifold, and that coordinate system has some very nice properties, okay? So, and especially when we're doing GR, when you don't know what your manifold is or what the curvature is, very often a very normal experiment to do would be to say, okay, I need a coordinate system. Let me sit in a lab somewhere locally, and I basically knock 3 things in 3 different directions that are normal to each other, and I watch them go on geodesics, because if you don't do anything to a particle, the straightest line it will follow is the geodesic. So one way of literally structuring your coordinate system is you let a whole bunch of particles go orthogonal to each other and you watch them, and that will then be a valid coordinate system. Okay, and you will find that the geodesics the particles move on will actually tell you something not only about your coordinate system locally, but about the curvature of the manifold, and we'll get to that later on. If you have a whole bunch of geodesics shot off together in some sense, roughly parallel to each other like that, the way they deviate from each other actually is measured by the Riemann tensor again, but we'll prove that maybe next time. Okay, so geodesics can be used to construct a coordinate system, the manifold. They are convenient for certain calculations, and what is also true is particles that are freely falling in a space-time actually follow geodesics as well. Now, to construct a coordinate system on a manifold, what we're going to do is we're going to define an exponential map. So if you remember when we were looking at dynamical systems, when we got close to our fixed points, all the trajectories we linearized about the fixed points, and then we got an exponential map that defined how something was moving close to a fixed point. Okay, so have that idea in mind. So exponential map is very useful when you start at one thing and you want to explore the stuff around it, around a known area. In manifolds, we can define an exponential map rigorously as follows. Let P be any point in your manifold, okay? And then we want to define a map from the tangent space at P to the manifold itself, okay? And the way we define that map is we literally take each tangent at the point P and we take it to a point in the manifold. So in other words, we're at P, we have all the possible tangents at P, and we're going to define a map that's going to take all those tangents to another point on your manifold. And the point we choose, okay, is that the point that we map P to is a point Q that lies one affine parameter distance along from P along the geodesic through through P. So you have point P, you have a vector that's part of your tangent space, okay? And the moment you have a point and its initial velocity or initial vector, then you can integrate the geodesic equations because they're a second order equation and they're uniquely determined by the initial condition. So then you integrate these equations for one affine parameter distance, and you say, fine, that's my new point on the manifold. Okay, so that's how you define the exponential map. Okay, and you can always do that, and it also is very, very useful, has useful properties. So you're literally then turning each tangent vector into a new point on your manifold. Okay, and then what you can show is there exists a small neighborhood near of the origin of VP, in other words, around P, on which the exponential map's defined. You can always get it because you can always integrate the geodesics and they're unique, and is one-to-one. So this is why you have to restrict it to a small neighborhood, because you can imagine that at least initially they all are going to move out. Okay, but there can be a situation where they actually cross each other or collide. But at least close to the point where you start, it can be one-to-one and invertible. And here is how it stops being to one-to-one. If the geodesics cross, and remember that is not allowed, or usually in ordinary ODEs, we say that the integral curves don't intersect each other. But we haven't proven that here yet. We've only shown locally, because you locally can map it to Rn. The geodesics don't intersect each other, but there's nothing to say wait long enough and they'll cross. If the geodesics cross, or a singularity is reached, so one place where the geodesics do cross is like the center of Schwarzschild, or the center of basically all the geodesics go in there if you're falling in radially. So that's a singularity. Okay, so if the geodesics cross, or a singularity is reached. So a singularity is where all the geodesics like crash into each other. It's possible for having weaker things where your geodesics cross, but it's not a singularity. Yes?
Can I ask something here?
Yeah.
Specifically to what my project is about, with the geodesic cross, can't we say, well, it is at the same point, but it's not the same point in time. So in the time coordinate, it differs.
But that's not crossing, right? Because if you're talking about a geodesic in a four-dimensional manifold, and you have one geodesic going through a point at time t, and another one going through a point at a later time, then in the manifold they haven't crossed. Okay, they've just passed each other by. They've passed by the same spot at different times. So that doesn't count as crossing. They appeared, their projection onto the r theta plane appeared to cross. And that's fine, that's allowed, because actually in the four-dimensional space they are missing each other like that. It's the same, if you can remember the Lorentz attractor, right? Those trajectories don't cross, but if you project them down into the xy plane, they look like they're doing this. Okay, so it has to actually intersect each other in the full dimensionality of your manifold to cross. Okay. If this happens, then your exponential map is no longer one-to-one. Okay, so the exponential map in the manifold is literally connected to your geodesics. It's pick an increment in your affine parameter and then you can basically map any single vector to a new point on the manifold where you've gone a fixed distance along the geodesic that started off with a tangent vector at that manifold. And that's actually, getting back to your project, that's also what you do basically if you have a round thing emitting light, right? If you have at a point P, you have a round source emitting light, you can emit light in every single possible tangent vector, okay? And then you can actually integrate your geodesics one step along those tangent vectors. If you're in flat space, what you would have gotten is just a sphere, right? You had one piece of light, one source of light, it emits it in every direction, it steps one distance away, and you basically get a sphere. If you are in curved space-time, in fact close to a black hole, not all the geodesics will continue to going straight out. Some of the geodesics will fall into the black hole, some of them will go out and then curve back, and then go back into the black hole. So there you can see, at least locally, it's going to look like a sphere, but when you get not very far from your source, you're going to have geodesics curving around and then going back into the black hole. And when you have the case where all your geodesics of the light that you emit falls into the black hole, in other words, turns around and goes to your singularity, then you're inside the event horizon. Okay. Okay, so your coordinate system fails that way. Okay, so your tangent vectors an element of an n-dimensional space, and so therefore can be identified with Rn, and your exponential map basically gives us a coordinate system that is centered at P, and this thing is called Riemann normal coordinates. Okay, so it's literally a coordinate system that arises simply from the fact that you are looking at your geodesics. So it's a coordinate system that is uniquely suited to your geometry. And one of the nice properties of this particular coordinate system is that its Christoffel symbols vanish. Okay, so remember, we've been, up until now, we've said we have a chart, if we have a chart, we have coordinates. If we work out the derivatives, we have a derivative operator associated with a chart, and if we have the derivative operator, we can get the Christoffel symbols, and then we can compute things. Okay, in Riemann normal coordinates, in other words, if you construct your coordinate system by literally focusing at a particular point and then integrating along the geodesics, you've got a coordinate system in which your Christoffel symbols vanish, but your curvature does not. So in other words, the Christoffel symbols vanish at that point, but the derivatives of the Christoffel symbols don't. And that you need to have, or that was actually built in, initially Einstein understood that, because what that means is that locally, you can literally, if you choose the right coordinates, you can make any manifold appear as if it's just a flat manifold in a small region around the point that you're looking at. Okay, so what Riemann normal coordinate systems does, it really gives you a way, or the experimenter a way, to set up a lab locally, to set up a coordinate system that's associated with that lab, and then to begin testing things in a manner that is going to look as flat as possible. Okay. In other words, you will still see acceleration. It will be like a lab on Earth. A lab on Earth, you like set it up, you have all your directions, you have one direction that's special because that's where gravity pulls down. Okay. But locally, if you shoot a trajectory out in any direction, you can just watch it and you can have your coordinate system. Okay. Where the curvature comes in, curvature always causes acceleration. So when you see your line starting to bend, then you know that you're not working in a flat lab, but you're actually working in one where your curves, where your space-time is bent. But that doesn't affect like your very close small measurements. That can still look exactly as if it were in flat space. And that is true at every single point in your actual manifold itself. And the way you construct that system is this thing. And I mean, Riemann is the same Riemann that made the tensor, the curvature tensor. So the reason he constructed these coordinates was he literally wanted the coordinate system in which, at a point, things were as simple as possible. Okay, so Riemann normal coordinates, basically at a point P, have the property that geodesics through P are mapped to straight lines through the origin of Rn. Okay, so not only do you have the Christoffel symbols vanish, but the actual geodesics themselves get mapped to straight lines once you've taken the chart to Rn. So that's why it is such a useful coordinate system. Okay, and if that happens, and this is basically deriving for you that the Christoffel symbols vanish, if you're mapping your geodesics, yes?
Sorry, so you have mapped straight lines, will it be then something like, if all of them go through the origin, will it be like concentric circles with lines going into the origin? Because if you think of the normal Cartesian plane, it's only the x and y axis that actually passes through the origin. Or how does every line go through the origin?
Because you've constructed the lines. You say at a point P, I'm going to find a coordinate system that's valid just around a little patch around point P. Okay? And what I'm then going to, and the way I'm going to do that is at every point, at point P, I'm going to have a vector that points there. In any direction you can have a vector. Then the way I define the coordinate system is the thing that takes point P one step along the geodesic that has that vector as a tangent space. Let's see if I've got a picture. Okay. So here you have at point P, you choose any vector, and then what the exponential map of P does is it takes this vector and it maps this point to a new point that goes along the geodesic over there. Okay. And it does, yes, do you have a question?
Oh no, I was just saying that's why you said free-falling particles fall like geodesics, because I mean it just seems the straight line on a manifold if you think about it.
Yes, it is a straight line to the manifold.
So it goes back to that previous lectures where we were mapping the neighborhood of a manifold into the Rn space.
Yes, we are literally, yeah, we are literally choosing a chart that maps the manifold around this point. In other words, everything on that circle, like one step from point P along a geodesic onto Rn. And the way we map it onto Rn is how far we've gone along the geodesic. Okay, so we basically choose vectors that form a basis for our what's a tangent space, and then we say let any point around here, we can say choose the vector that points in a direction and then map it along the geodesic to the geodesic that has that vector as its tangent to a new point in the tangent space. So you literally can say all the points, say, that lie on this part of the manifold around there, you can reach by this means, and you can reach it by a line that goes along the vector. And if you then take that to Rn, what you're basically doing is you're choosing a direction and then choosing your coordinate to be the parameter along that direction. Okay, so you're not talking about the whole plane, you're just talking about lines that go near the origin, and the origin is the point where you're mapping from. So you're literally going to choose a whole bunch of points, make a whole bunch of overlapping charts to actually cover the whole manifold. But the thing is here, you only live in the region of one point. Okay, so then you basically choose a map that's valid around where you are conducting your experiments. Okay, so where am I? Okay, so they basically have the property that all the geodesics through P are mapped to straight lines through the origin in Rn. Okay, But if that is true, then if you have straight lines, then the second derivative will always vanish. Okay? And what that means that at your particular point P, all these Christoffel symbols must be 0. Okay, so by watching geodesics, you basically have a situation where the particle will freely flow along there, therefore the connection is 0 when you move from this point to that point. Okay, so if you have Riemann normal coordinates for conducting your experiment, at least all velocities or the initial directions close to the origin will look exactly as if it looks in a flat space. Okay, when you move away from your origin, you'll see they start accelerating, doing strange things, and that tells you what the curvature is. Okay, we are going to see that again after a while. Okay, so this thing is basically useful for calculations because generally in a curved manifold, and the reason it's useful for calculations is because if you have calculations that occur just at one point or just around one point, what you can do is you can say, and they're messy, like you have lots of Christoffel symbols and stuff. You can say, let's transform to Riemann normal coordinates. Let's do the calculation. And as long as the calculation is a scalar or something that's not a tensor, or is a scalar, you can get an answer, and then you can transform it to any other coordinate system. Okay, so it actually, in some cases, it makes calculations really, really easy. So, and one place where they use it a lot is where you have particles that collide. Okay, so particles that, if you sit there and you watch a pair of particles moving very rapidly and then colliding, it's very, very complicated physics to do. Okay, but if you transform into the rest frame of the two particles, the center mass frame of the two particles, then the collision becomes simpler. And then what you do is you say, okay, let's work out the conservation of energy and conservation of mass of the collision in that rest frame. So that becomes one problem. And then it's easier because all these things tend to vanish. And then you go back and you transform your answer into something that you'll see from a different coordinate system. Okay, but I'm not going to do the details, but that's a place where it's actually used a lot. You only have to get an answer for certain things in one coordinate system, and if it's a tensor equation, it remains true in any coordinate system. And that's where these guys come in. Okay, so I want you to know about them. I don't think we're actually going to use them. Okay, so generally, even though you can set these guys to 0, the derivatives of them are not, because generally you're not working in a flat space, you're working in a curved manifold. So what this thing does is basically it lets your coordinate system look as flat as possible, but it doesn't restrict the manifold that you're in. Okay, so that's one set of coordinates. Another set of coordinates, and that the Riemann normal coordinates is set at a point and everything is geodesic going out. Another set of coordinates that are very useful and that people use when they do these numerical relativity simulations. Yes?
Is there something about acceleration and curvature? It doesn't mean something. Could you just explain a bit about it?
Okay, so far I haven't explained it. I will come to it. But I'll tell you what it does. So far we've had that curvature measures the failure of two derivatives to commute. Curvature also measures if you parallel transport a vector around a closed loop and you come back, then you have another vector. It measures the change of that vector. Okay. The third thing the Riemann tensor does, if you start with a whole bunch of geodesics, say for example you have one geodesic that goes this way and you have affine parameters along it. And then at each affine parameter, you take a whole bunch of geodesics and you shoot them off at 90 degrees to the original one, or so that the dot product with the original one is 0. Okay, then you have a whole bunch of lines going like this. Okay, what you then can measure is whether these lines, in some sense, if they go parallel, they're in flat space. And if they like depart from each other and come back, you can prove that departure from each other, or they call it geodesic deviation, is also entirely contained in the Riemann tensor. Okay, so curvature also measures literally how the geodesics move from each other, but that I'll do the next time. Okay, so let's now start with the second type of coordinates. If you're given a metric and an associate derivative operator, and these things are what they call synchronous coordinates, okay? And to describe them, we need the idea of immersed submanifold of M. Okay, so remember when we did 3 dimensions and the paper, we worked in 3 dimensions, and then the paper was inside the 3 dimensions, okay? And so, but we could measure distance along the paper, but that distance we could also measure from the 3-dimensional manifold. And then I said, this is not a complete picture. You must not think of every manifold as being inside another one, okay? And up until now, all the stuff that we've done has had, it's been entirely just to do with the manifold. We haven't assumed anything outside of the manifold. All of it has been, you have the point, you have the tangent space. It's all been constructed associated with the manifold itself. But the idea that you can have a manifold and then a manifold inside, that definitely exists. And this is what we're going to start developing now. Okay, so an immersed submanifold of M is a manifold with dimension smaller than the dimension of M. Okay, so the N is the dimension of M, and M tilde is the dimension of the manifold. Okay, and we say it's immersed if there's a function that maps the manifold with a smaller dimension to M, and that's C infinity. Okay, and that function is locally one-to-one. Okay, so what that basically means is for each Q in S, it has an open neighborhood O such that phi restricted to O is one-to-one. Okay, and therefore the inverse exists. In other words, the inverse applied to the image of O can actually map it back to S. Okay, and that's also C infinity. Okay, and then phi of S is an immersed submanifold of M. Okay, so for example, an example of an immersed submanifold of M is just this page. Okay, that's actually, suppose you have a surface in Rn, that is immersed submanifold of M, but it's more than that because you can put the total manifold in the higher dimensional N. Okay, look, this thing doesn't require that. Okay, it simply requires that for each Q in S, there's an open neighborhood and there's a function that restricts, that is one-to-one there. So this thing means that you can have bits of a manifold being mapped into M. Okay, there's another definition, which is an embedded submanifold of M. So this is actually what the piece of paper is. And it differs from the immersed submanifold by the following things. An embedded submanifold is an immersed submanifold with the additional condition that phi of S is globally one-to-one. Okay, and that is that phi applied to S does not intersect itself. So there are two things, okay? The normal thing that we talk about is a sheet, like the sheet of paper in R3 is an embedded submanifold. It's a subset of the bigger manifold, and you can globally put it in. Okay, an immersed manifold is one where locally you can find a map that puts it in, but you can't necessarily put the whole manifold into Rn. An example, and so now the thing is, not all manifolds can be embedded in another manifold. Even if you look at two manifolds, not all two manifolds can be embedded in R3. In fact, the example in your tutorial, that Lobachevsky plane, you can never put the whole of that manifold into R3. You can put little bits of it into R3 and look at it and study it, but you can never embed the whole manifold into R3. Okay. Whereas you can, and when you put the little bits in and you study it, you do this, you basically have a chart that is in the neighborhood, in an open neighborhood where this thing works. Okay. And if you want to think about how this is possible, suppose you had a manifold that has the property that it looks like a vuvuzela, right? It is a manifold, you can specify its curvature, and the thing is, eventually when it reaches a certain point, it's curving fast enough or increasing fast enough that you cannot put that into R3. In other words, it's actually increasing its circumference, its relationships between its circumference and its area so quickly that there's no way that you can get an object in R3 that will actually do that. Okay? And that's what that Lobachevsky plane actually does. So that manifold you cannot globally embed in R2 or in R3, but you can look at parts of it. You can always go to one point in the manifold and say, I want to make my local chart around that point, and that you can put in R3. And so there are weird things that can happen. For example, around Kerr and Schwarzschild, sometimes the space gets curved so strangely you can also not embed it in some manifolds. And people then go about and study for a given set of manifolds into which higher dimensional spaces you can put them. And there's a theorem that says any two manifold, so any two metric, you cannot embed it into R3 if the curvature goes negative. Okay, if there's a bound on the curvature, and the curvature always stays positive, you can often put it into R3. If the curvature goes negative, you can't put it into R3, but if you can always put any two manifold embedded into R5. Okay, so there are strange things that you can specify the geometry of the manifold, and then you can ask, can I put it into this other manifold? And sometimes the answer is yes, and sometimes the answer is no. And so that's why I said at the beginning, be careful of simply viewing a manifold as something that lives in R3, or a two manifold as something that lives in R3, because it can't always. Okay, so now we want to get another thing, another concept, and we call that a hypersurface of a manifold. And a hypersurface appears often when we work in relativity. Okay, so a hypersurface is an n-1 dimensional submanifold of M, okay, that has dimensionality M. Okay, so there's two things. If you have M, you can always say, I want to study everything with a certain, say, coordinate, and that will give me a hypersurface, in other words, a thing that's in -1 dimension, and this thing is always embedded in M because it was literally structured by choosing a slice of M, so that's fine. Okay, these other things occur when you take a random manifold and you say, can I put it into another one? Okay, so there's two different concepts. So the hypersurface is as follows. If you have any point P in your hypersurface, you have a tangent space associated with P that's inside the hypersurface, okay? And then it's n-1 dimensional because your hypersurface is n-1 dimensional, and your tangent space always has the same dimensionality as your hypersurface. And it is also a subspace of the tangent space of your full thing. Okay. And therefore, the one vector that is in the tangent space of M, but is not in the tangent space of your hypersurface, is what we call the normal vector. Okay. And that normal vector is just basically a direction, so it's unique up to scaling. Okay, and that thing is orthogonal with respect to the metric to all vectors in the tangent space of your hypersurface. So here your concept of you have, say, an n-dimensional space, you have a surface inside, you call that surface sigma, okay, and then within sigma you have a tangent space, and then you have, and that makes up, at a particular point, you have the tangent space within sigma, and you have the normal vector to sigma, okay? So that all those concepts are exactly what you normally think they are, okay? And now it goes on, if your metric is Riemannian, and by Riemannian I mean that if you diagonalize the metric, all the eigenvalues are positive. Okay, so that's a Riemannian metric. Then your normal vector is never in the tangent space of your embedded manifold. Okay, if your metric has indefinite signature, and that's true of Lorentzian metrics, okay, then n could be null. In other words, n dotted with n a up times g down, okay? That could be null. In other words, it could be 0, and in fact that's what light rays actually does. In other words, you could get this condition. Then what you have is that n up is in fact an element of your tangent space of your hypersurface, okay? But the dot product is still 0. So the condition that determines n, okay, is that it's basically orthogonal to all the vectors inside the tangent space, but if all the vectors inside the tangent space are null, it can actually lie in the tangent space. Okay, if this is true, then sigma is a null hypersurface at P. Okay, and that is literally like it's the path that light will follow. We very seldom work with this. We tend to work with things in which you actually point to a normal space-like surface. So these things are weird to me, where the actual normal vector lies in this tangent space. Okay, if n is nowhere null, okay, you can normalize it with this condition that n up, g, a, b is equals to plus minus 1. Okay, and that's the normal vector. When it's plus 1, it's basically our time-like vector. Okay, so what we have, just here's a picture. We have a manifold. We have a hypersurface within the manifold that we call sigma. So it's sort of a slice of the manifold. And then what we do is we can define another coordinate system where you sit on this manifold, and for every single point on the manifold, you say at that point, let's work out the normal vector, and let us shoot geodesics out along the normal vector. And then I say, if I've gone one step or one affine parameter along the normal vector, then I get my new manifold or my new hypersurface. Okay, so what you're doing there is you're literally taking one slice. You start, and we do this whenever, the way we think about time in relativity is exactly this. You take one surface, and you call that a hypersurface. You have a coordinates, and that's like your 3 space. Like at this snapshot in time, you have the surface. You have coordinates, spatial coordinates on it. Then you say, one time step later, I want to have a new surface. So then at each point, you say, what's normal to the hypersurface over here? You have a normal vector pointing out. You take one step along it, and then you get a new slice. So you're literally mapping every point over here to a point on the thing at a time step a little bit later. And when we do the numerical relativity code to actually integrate the black holes, this is exactly what we're doing. Okay, we're literally using the curvature, or the definition of our curvature, to actually take an initial time slice and step it forward. Okay, consistent with the prescription. And that's a really hard problem. But the coordinates, one way of choosing coordinates is simply for each point P and Q, you choose the normal vector, you have the geodesic that points along there, and then the next slice is taking a step T along the geodesics. Okay, and this is true for non-null hypersurfaces sigma. Okay, so for all point in sigma, construct gamma P, which is the geodesic that goes through the point, okay, and has the tangent vector associated with a normal vector. So these things are simply your geodesics. And then choose coordinates on sigma, in other words, the n-1 coordinates on sigma. And then in the neighborhood of sigma, you can say, okay, right, let's label each point R by the parameter T along the geodesic. So the moment you step off the slice, you can say at that point, you can say, okay, it's the point that you've stepped a distance T along the slice, and you start along the geodesic that started at P. Okay, so it's a new way of connecting the coordinates on this slice with coordinates at a later time. Okay, right. So another use of geodesics. Okay, so what that basically does is it takes all these coordinates here and it maps them to fill the space. Okay, once again, if the geodesics happen to collide, and this is what causes the people that do numerical relativity absolute nightmares, is then your coordinate system fails and your code crashes, and then you want to find another problem.
That's actually what I wanted to ask right now.
If they cross, this thing only works until they cross.
Yeah.
Okay, so then you can do and say, okay, fine. One way of thinking about it, suppose I pick a flat surface like this, and I pick all my geodesics up. Then I'm going to have a whole bunch of stack of papers stacked up. If I choose a surface that's going to do like this, and I choose my normal coordinates, it's going to work just for a little bit along the surface. So it actually matters how you choose this initial hypersurface if you use this method. This is not the only way of specifying coordinates, right? You can say, let me have this hypersurface, and at a later point I have another slice, and I don't have to map it along a geodesic. I can map this point to that point. So there are other ways of doing it. The geodesics are just convenient because it actually allows you to prescribe where you go based only on this previous one. Okay, so yeah, if this happens, there are tricks to go past it. And the guy that worked out most of them, or did the formulation that you had actually a well-defined mathematical system, is called Jimmy York. I think he's passed away. He was a weird cowboy southern guy. Totally not like if you had the idea, your like idea of what a mathematician is, like the very careful guy with the thick glasses and the very precise. This guy was not that, but he was absolutely brilliant. He was a drunk. He fought with people. He basically could beat them up. But he had a very clean mind when it came to... Huh? Yeah, it's like he took all his energy.
A little bit madness inside of
it's like he organized the life around the Einstein field equations, like to perfection, and then everything else sometimes fell off the wagon. Very interesting guy if you could get him at the right time. But he really, without him and another lady, it was weird. It was Jimmy York and another lady, Chaucret Brouard, a French lady. Very, very good mathematician, very, very proper. In fact, one of the books that's in the course was written by her. Understood the field equations more deeply than anybody else. she and him worked together. It was the most unlikely couple of people that worked together. And they did beautiful work. I mean, without them, we would not be colliding black holes. Literally, without them, we would not understand how you go from one slice to the next slice if you can't do this. So they did the full general formulation. It's really, really nice. Right. Okay, so in Gaussian normal coordinates, the geodesics remain orthogonal to all hypersurfaces because you basically constructed the next hypersurface, right, by taking the geodesic along here. And remember, the reason why that is so is you've parallel transported your tangent vector. So if you have a tangent vector over here, you parallel transport it to over there. This thing, your tangent vector, is still pointing in the normal direction of the next surface. Okay, so it's a very nice construction. Okay, and right. Okay, so what this is basically, it's true if sigma equals to sigma 0, and to prove this, you basically say it's true if sigma equals to sigma 0, okay, and you want to prove that the tangent vector is still the normal vector for sigma t, and the way you do that is basically you show that the geodesic tangent field in A remains orthogonal to all coordinates in the basis fields, okay. And so so you can basically do this. The way you do it is you start on your slice, you work out all those basis coordinates that's dependent on the coordinates you chose here for your initial slice, okay, and then you use them to generate the tangent space at a later time. Okay, and the way you do that is let XA be one of these fields. In other words, all the the element of the tangent field to sigma, okay, and you literally take it here, so this XA is pointing within sigma, you then go and you parallel transport it to the next place, okay. So what you basically say is you have the normal vector, the parallel transport operator applied to the dot of XA with a normal vector, and what you then get is simply writing out Leibniz's rule. You get that this is equals to NB, right, times NA times the derivative with respect to B of XA, okay. And the second one where you have NA, gradient of NA, that is 0 because of the geodesic equation. And then, so what you then have is that this guy is actually equals to XB, the gradient of NA, okay, since the elements of the coordinate basis on M commute, okay. And so what that means is that if you start with your basis vectors over here, okay, you look for the next one, the next set of basis vectors over there is exactly the same ones as you had there, and the normal vector also remains the same. Okay, so what you then have is that this thing is equals to a half XB times the gradient of B, NA dotted in with NA, okay, and once again using Leibniz's rule, you have, because NA dotted in with NA was chosen to be normalized, you have that thing is 0. Okay, and so what you have is the property that these the basis vectors over here, because you're moving, are exactly the same as the basis vectors in the manifold over there. Okay. So that's something to remember. Don't worry about this too much now, But just know that you can actually use the geodesics to connect one set of coordinates on one slice with a set of coordinates on a second slice. What I wanted to do in the next half an hour is just give you another feel for what geodesics are. So we've had that they parallel transport along themselves. They behave like straight lines. Now there's another concept, is that they are the shortest curve between, or the extremal curve between 2 points. Like if you were to pick a different curve that's not geodesic, you will always be following a longer path than if you just follow the geodesic itself. Okay. So to work out that property, we once again need the definition of the length of the curve. And that's very similar to what we were doing in our three-dimensional case. So if you have a smooth curve C and a tangent vector TA, okay, and a parameter along the curve, okay, and you're on a manifold and you have a Riemannian metric, okay. By Riemannian, remember, if you diagonalize this metric, then you get positive eigenvectors on the diagonal, okay. The length L along a curve is simply defined by the integral of the tangent vector basically dotted in with the lower version of the tangent vector. So you have the two tangent vectors fully contracted with your metric. Okay, so that's the definition of your inner product. That's exactly the same if you work in a flat metric with what we did with when we worked out the parameterization along our curve in 3 space. Remember, we spoke about the arc length parameterization. We literally dotted in the tangent vector of the thing with itself. This is just the generalization of that. So you literally say, and this is just basically Pythagoras' rule generalized. So you literally have your tangent vector contracted with a metric, and you take the square root of it. And that's the length of the curve. Okay? If you have a Lorentzian metric, this is what we get in GR, where one of the metric components, if you diagonalize it, is negative. Okay? Then you have, say, for example, a signature where you have minus plus plus or minus minus plus plus or something. Then you have 3 possibilities. Okay? The curve is called time-like if GAB of TATB is less than 0 everywhere. Okay? The curve is called null if the tangent, and this is like the null geodesics, if GAB TAB is equals to everywhere. And the curve is called space-like if GAB TAB is greater than 0. Okay, we don't tend to work with that because physically you can't move along them. Okay.
Is that why I use time-like and you use null?
Yeah. So the null describes how light travels,
yes,
and time-like describes how particles travel. Okay. But yeah, let's leave that one for a while. Huh?
What does it describe, that one, the space-like?
I don't know. I mean, space-like, it's basically would require you to be at 2 places at the same time. It doesn't make sense. Okay, so no, I don't know.
No, I'm just joking.
So time-like is basically start at 2 points. You start at a point, and then you travel forward in time, and you're gonna, and possibly position, and you get to a new point. Okay. Space-like, I don't know.
I'm thinking about another cone thing in memory.
Yeah.
So would it be a point that lies outside that? If you have 1 point here and 1.
No.
So you'd have to travel faster than light to get to that point.
Yeah, it might be messed up with that. I don't know. Either faster or light or backwards in time. But yeah, I know I've only worked with these 2. For space-like curves, okay, that's the definition. Yeah, I think space-like is if you travel at a fixed time if you move. So that's a problem. For space-like curves, it basically assumes that your time, you're not changing time. Okay, so no particle can be at this point and at that, travel between this point and that point without changing time. So that's why we tend not to use it, is because it's like you have something at two positions at the same time, you're not going to travel between them. No physical thing that we know of is actually going to do that. So they might use it when you start doing quantum mechanics and you have other possibilities, but no, I don't. In classical gravity, I don't know of anything that has a space-like trajectory. Okay, so for time-like curves, you basically have the proper time, which we say is, so the problem with the time-like curves is it's negative, so in order, when you work out the proper time, you don't want to take the square root of a negative number. So you literally say minus g ta tb, and that's like your local clock that's going along it. The length of curves changing type is not defined. Okay, so you can imagine if you have a certain, all you've described is a curve with a tangent vector, you can imagine your tangent vector can change. It can become, it can be time-like at one point, and then you can move really, really fast, and you can approach the speed of light, and you can become null. Okay, so that type of thing, it's not defined with what we have. The one thing you do have is if you have geodesics, you can actually prove that the tangent, just where the tangent vector is parallel transported, whether it's a null or time-like or space-like, it preserves the norm. So if you have a vector that is time-like at the starting point and you move along a geodesic, then it remains time-like. So you can never have a particle becoming a light ray, and you can never have a light ray becoming a particle. So that's what it basically says. So for geodesics, which is what we're going to be focusing on for the most, we don't have this possibility that your contraction changes sign. Okay, and that's a good thing because then we wouldn't know what to do. Okay. So geodesics don't change type, and if we have, suppose now we have a curve parameter. Suppose the curve parameter of C is changed. So suppose now, remember right also when we were working with the origami stuff, we had this idea that you could change your parameter from S to some other parameter. And in fact, sometimes it's useful, like with Mino time, to work with something or that is not affine. And even when we did that problem with a parabola, it was easier to do the calculation in a parameter that was not the arc length parameterization. And so if you do that, let's just look at the impact of that. So suppose you have a new parameter that is simply a function of t. Okay, the new tangent vector S is simply the old tangent vector rescaled. Okay, so that you should know. The vector is still, in some sense, tangent to the curve, but the norm of it changes as you rescale the parameterization. Okay. And so, but the interesting thing is, suppose you have measured length, okay, the length along a curve, using the new parameterization. In other words, you have GAB, SA, SB to the half times ds rather than dt. What you can do is you can go, so that's the length in the new parameterization. You can then go and you can change variables back, okay, and what you're going to have is that is in fact, this integral is exactly equals to that integral. Can you see why? That's actually important. So suppose you start with this integral, you replace SA with TA times dt ds. Okay, so you're going to have TA times dt ds and TB times the TDS. So you're going to have the TDS squared. You're going to take the square root of that thing. And so then you can take it out of the square root. So you're going to have GAB dt ds times ds, which is just dt. So literally, even though you've parameterized it with a different parameter, this definition for arc length is actually doesn't change, right? Whether if you work out the arc length using your new parameterized curve and you work out the arc length using the affine parameterized curve, you're still going to get the same answer.
So are we just doing it because one integral is going to be simpler than the other? So it's basically just trying to make the math simpler, or why are we doing
I'm just showing this to you because this is true only for the length. Like remember when with our curves that we worked in for the origami, the parameterization, we could always work out the length. But if you worked not in the arc length parameterization and you tried to work out the curvature, it didn't work so well. Okay. So usually you are careful if you change parameterization. I'm just saying in the case where we're working out the length with this formula, it doesn't matter what your parameterization of the curve is. Okay, so what we now want is a condition on a curve that makes it extreme. In other words, that makes it either the maximum or the minimum possible length that you can achieve. Okay, and we want it to be the extreme length between its endpoints. And then we want to say, fine, let's find the curve whose length doesn't change. Okay, to first order under arbitrary smooth deformation. So suppose now we have 2 points. Okay, and the reason this might be useful, it might find me a way of finding a cute way past your problem. You have 2 points. You want to have a curve that you go from one point to the other point in the manifold, such that when you work out this integral along the curve, you have the minimum possible distance between the 2 points, or the minimum possible length change between the 2 points. How do you do that? Okay, so in flat space, it's just a straight line. What we now want to do is we actually want to connect it with geodesics. You can. There's a very clever way of studying this problem that was actually known way before manifolds was developed. Okay, so this problem appears a lot. Suppose you have a ball rolling on a strange. So one place where this problem occurs is suppose you have 2 soap bubble blowing things. You know those things where you like blow the soap bubble. And suppose you have a soap film and you put 2 of them together and you move it apart. Okay, what shape is it going to take? It's going to do not quite. Not quite. Almost, but not quite. It's going to take the shape that the surface tension becomes the minimum.
So basically minimizing the energy of that.
You need a way of solving the problem. Yeah. Okay. In fact, it's going to get the minimum, and what you mean by that is if you change the thing, if you push the shape a little bit, what it's going to do, it's going to pull tight. Okay, so in some sense you want the minimum energy, and I'm putting it abstractly because it isn't actually an energy. You want a minimum energy in the surface itself. In other words, you want the surface so that if you push the surface a little bit, it's eventually going to have a bigger, let's say, energy or measure than the optimal one. Okay, how do you choose that? And so another problem is, suppose you have a string and you have a whole bunch of obstacles for the string. So like suppose you have mountains and you have things, you have a geometry, and you put the string in there and you want to work out the minimum way of traveling. Or suppose you have a mountain range, okay? And you want to walk from the one point to the other point following the minimum distance. So you have your hills do this. how do you choose that distance? Okay, so if you're very fit, what you would do is you would walk one path to the other point and you would measure the distance. Okay, then you would say, let me walk a different path, and if it is a shorter path, then it's a better path. Okay, and you measure the distance, and you could keep going like this until eventually you get to the path that is shorter than all the other paths you've walked, and you say, sharp, that's where I'm stopping. Okay, so when we have problems like that, they were studied by Euler and Lagrange in the 1800s. And they were very well known even before Riemann came around. And that problem we call calculus of variations. In other words, how we derive the equations that govern that is a whole study. And it's a very beautiful study in how you actually use a problem set up to derive equations rather than specifying the equations themselves. Have you guys ever seen that? Judith? Huh? Do you know what a Lagrangian is?
I've seen it somewhere in classical mechanics work.
Yeah, so it was done in classical mechanics first. Have you seen it?
Yes, but not in very depth. But yes, I've worked with it.
And you haven't?
I did it.
And you not either?
I did it.
You have done it?
Yeah.
Okay. I think what I'm going to do then is I'm going to I'll make a video on it, okay, that explains it and explains the part that's relative to the course. And then you can watch it or you can not watch it depending on what you want to do. What it basically does is it was developed in the 1750s, so it's ancient. And what it does, and this is where the connection, remember I said there was a Hamiltonian formalism for the geodesic equations that I derived for you. There's a way of connecting the Hamiltonian and this way of thinking about it. What it does, it goes about and it considers a general set of coordinates and their derivatives. And then it says, if I have any function that is a function of the time, the coordinates, and their derivatives, okay, what equations must these things obey so that I optimize the integral? Okay, so that's where calculus of variation starts. And what you can do through a very, very clever argument, you can eventually write down equations for Q and Q dot that they obey so that this integral is optimized. Okay, and it turns out that those equations that you get for L will give you the geodesic equations if you choose L to be this thing. Okay, the two are the same. So not only do the geodesics basically parallel transport according to themselves, and not only do the geodesics have all these other nice properties, they simply by that local condition, the equations, you are actually choosing the optimal paths between 2 points if the thing that you're minimizing is the length. Okay, so I'll go and derive the Euler-Lagrange equations. This is what they are. Let me just give them to you. Suppose you have this thing, this integral between 2 points that you want to optimize, and the thing depends on any function. So it's much more general than just geodesics. They were using it in mechanics a lot. Okay, what you want to do is you want to seek these things so that this path is optimized. Okay, and if you go through the argument that I'll make the video of, because I actually want to keep it, then what you eventually get is that these things, Q and Q dot, must obey these equations. Okay, in other words, you take whatever's inside, you take its derivative with respect to Q, okay, and you take its partial derivative with respect to q, and you subtract the partial derivative of L with respect to q dot, and you take the time derivative of that. Okay, so you literally start with that L that's defined, work out these equations, and then what you get is exactly your geodesic equations. Okay, and that I'll prove to you. But that is actually very useful because it allows you a different way to get your Christoffel symbols as well. So you actually have two independent ways of getting your geodesic equations. The one is parallel transport, and the other one is the Euler-Lagrange equations, the optimization of the path, the length between the 2 points. Okay, so I will look at that in a little bit more detail. If you needed to do the problem set, do look at the video. If you don't, you should be able to do it without it as well. But this concept that your geodesics are your shortest paths is exceedingly useful. Okay, and it at least connects, gives you a really a strong feel for what the geodesics actually do as well. Right, that is it from me for today. What's going to happen now? Yes?
Yeah, just quick, just the one before this one, this slide. Yes, so there we with Riemannian metric, and then the slide before this one, there was again this Riemannian metric, and the one time Prof said the eigenvalues is all of them negative.